Okay, we are up to Wednesday, August 3rd for Math 0324. And even though we have 3 homeworks today, 17, 18, and 19, I think the last one's not very long at all. I guess we'll find out when we get in there. 17, exponential functions, only 7 problems here. Okay, solve the given equation for x. So in exponential equations, you have a base that's a number, and the x is somewhere up in the exponent. When usually everything up to this point in math has been the other way around. Usually it's something like x squared, where the x is the base and the exponent's a number, or x to the 5th power. So now things are reversed. It's 2 to the x or 5 to the x. That's exponential when the base is a number and the exponent has an x. So what you hope happens is what happened here in number 1. You hope that these bases are the same or could be made to be the same. So I have 9 to the 2x minus 2 equals 9. Oh, I said that wrong. It's 2 minus 2x, and then 6x minus 7. So the x is actually in the back here. So if the bases are the same, or you can make them the same, which isn't always the case, but if you can, then the bases cancel out. Because if 2 powers are going to be equal, if the bases are the same, the exponents would have to be the same too. So that's really all that's happening, is you're saying the exponents have to equal each other anytime the bases are the same. And then you're just solving for x in a normal fashion. Get the x's on one side and the numbers on the other. Add 7. And again, these may or may not come out exactly. That's okay. Divide by 8. 9 doesn't divide by 8, but we'll just leave it like that, 9 over 8. Type a fraction or an integer, simplify your answer. So 9 over 8 doesn't simplify, but that is a fraction. And they'll do that sometimes just to make sure you don't guess and check the answer. Nobody would ever guess 9 divided by 8. Okay, what if the bases are not the same? Okay, I guess here's the opposite case. What if the exponents are the same? Then they would cancel out. So powers can only be equal if their bases and exponents are both equal. So if I have a 5x plus 12 cubed, this is number 2, and then it's equal to another power that's got 64x to the 3rd. I guess the only issue is that 64 is not in there. So if there would have been parentheses around this, then in essence the exponents would cancel. One thing you could think of to say that they cancel, the reason they cancel is the opposite of a third power is a third root. So I could do a cube root of both sides. And this would make them both cancel. Then the power would cancel the root. And then in this case, I need to write 64 as with a 3 exponent. So it turns out that's a 4. 4 to the 1st is 4. 4 squared is 16. And 4 to the 3rd is 64. So we'd want to write this one as 4 to the 3rd, x to the 3rd. If things are multiplied or divided together and they both have the same exponent, that's the same as 4x in parentheses to the 3rd. And that's the idea, is it's not going to cancel out unless the whole thing has that same exponent. So this exponent can cancel that one. So we're left with 5x plus 12 equals 4x. And you could, the shortest amount of work here would be subtract the 5x, even though it'll make the x negative. At least you can get x's on one side, numbers on the other in one step instead of 2 steps. 4x minus 5x is negative 1x, literally, even though we don't normally write it that way. But you need to divide by negative 1 to get x totally by itself. So negative 12 equals x. Simplify your answer, use comma. They don't want to give away how many answers there are. Negative 12. It says use a comma to separate answers, but we only got one answer. Okay, what if you can't make the bases the same? Number 3 is like number 1, except you can't make the or you can make the base the same, but they're not already the same the way number 1, they were already both 9s. But in number 3, one base is a 16 and the other one's a 4. They don't cancel out if they're different. And then this side's got an x, and in essence, this one's got a 1 for its exponent. So there's 2 ways this can end. One is you hope that you could make the bigger base look like the smaller one. And if not, we could change them both to something else or employ another strategy. But we can make 16 look like a 4 because right here, 4 squared is 16. So I can change 16 to literally be 4 squared. Just for the sole purpose of making the bases the same. So I'm replacing the 16 with a 4 squared. The x is still there as an exponent. And the bases don't quite cancel out yet. You need to employ a rule of exponents. I think we talked about the rules of exponents in here. When you have a single base and 2 exponents, a double exponent, that's when you multiply the exponents together. And 2 times x is literally 2x. So after these 2 steps, now I'm finally where number 1 started. And the bases cancel out because they're the same, and I've already gotten the exponents situated. So you're just left with this, 2x equals 1. Divide by 2, x is a half. One half, that's an integer or a simplified fraction. Okay, similar deal here on number 4. 2 to the 2x minus 5 equals 16. I can make 16 look like a 2, actually. So you probably can't do that in your head, but it's okay. 2 to the 2x minus 5 equals 16. The goal is to make 16 look like a 2. So start listing the powers of 2. 2 to the first is 2. Anything to the first is itself. 2 squared is 4. 2 cubed is 8. 2 to the fourth. 2 times 2 times 2 times 2, that's 16. That's the one. So replace the 16 with a 2 to the fourth. And then the bases are the same. The exponents are situated, so we can cross out the bases. 2x minus 5 equals 4 is all that's left. Add 5. 2x equals 9. Divide by 2. And again, they like simplified fractions. 9 divided by 2, it doesn't divide, but it doesn't reduce either. So they're just going to want you to leave it like that, 9 divided by 2. Okay, x squared equals 100. Now this is different. Now the x is back down in the main level where you're used to it being. This is not a number to an x power. This is what I was saying at the start. You're more used to this in other math classes. So this gets solved differently. Number 5, x squared equals 100. this sort of is like, do I have that right? Yeah, x squared equals 100. This is like the one where I did a cube root on each side. If you have a exponent, a number exponent, you want to get rid of it, you need the same root as that exponent. So the opposite of a square is a square root, which is really a 2. They normally don't write it, but it is a 2. So a square and a square root cancel out, and you're left with just x. Now, literally what a square root means is what number times itself equals that value. What times itself equals 100? Well, 10 times 10 equals 100. So that's why the square root of 100 is 10. Or you could say there's a pair of 10s in here. 10 times 10 makes 100. And when you have a pair on the inside of a square root, you get to have one of those on the outside. The only issue is a negative times a negative is a positive also. So a negative 10 times a negative 10 also makes positive 100. So if you ever put a square root on each side of an equation, one side, usually where the number part is, needs to be plus or minus. It's a technicality that matters, and it's because negative 10 times negative 10 also makes 100 happen. So this is why there's two answers, and this is where they would want you to put 10, comma, negative 10, where you're listing your answers. Remember how it said separate answers with a comma as needed? This is where it's needed. Separate answers as needed. Use a comma to separate answers. So it's both 10, comma, and negative 10. That's not a coordinate. That's just squigglies mean I'm listing my solution set. So without the negative 10, they would have counted that wrong. And another way of thinking about it too is when you get answers, you can check them by plugging them back into the equation. If I plug 10 right where that x is, 10 squared equals 100, because 10 times 10 is 100. If I plug negative 10 in, negative 10 squared, negative 10 times negative 10 is also 100. Okay, then you get fractional exponents. So first of all, the same idea of this is going to apply here because I have an x for the base, not an x in the exponent. X to the 5 halves equals 243. So I want to get rid of the 5 halves. I have to do the opposite root, and it's going to be a square root eventually. But let me write it this way first. Actually, I just thought of this. I'm going to do the opposite fractional exponent to both sides of the equation, because that's the rule where you multiply exponents. And you'll get 5 times 2 is 10, 2 times 5 is 10. That'll literally be 10 over 10. That'll be x to the 10 over 10, which is x to the first. And that's the ultimate goal in algebra, is get x by itself. Now it turns out that fractional exponents can be radicals, which is why I was starting to write that, but you needed to do this first and get the x isolated. But then this 2/5, it's the denominator of the fraction that goes in the root. So there's a 5th root, doesn't look like a 5 very well, 5th root of 243 squared. And a good way to remember that is if you cover up the fraction with your hand, the bottom part of the fraction, the part that makes it look like a fraction, if you cover up the bottom so it doesn't look like there's a fraction there, it looks like 243 squared. That's 243 squared right there. It's the divided by 5 that causes this root to happen. And then it turns out you can do this either way. It's just that it's usually easier to do the root first, just because if you do the square first, it's ginormous. 243 squared is 59,000. So I wouldn't do the square first, just because how am I going to do the 5th root of 59,000? It's so large. So 243, that's 2, 4, and 3. 2 plus 4 plus 3 is 9. If the sum of all the numbers divides by 3, then this number divides by 3. 243 divides by 3. 81 times. Now, if we were doing square roots, then I would say 81 is 9 times 9, and that's a pair of 9s. If you were doing a square root, you'd have a pair of 9s with a 3 left over. But that's when you need 2 of the same thing. I need 5 of the same thing with this 5th root here. And luckily, I'm going to get 5 things because each of these 9s is 3 times 3. It takes all 5 of these 3s just to bring 1 3 to the outside. And then you still have your square here. So the final answer is going to be 3 squared, or 9. So a 5th root is also a 1/5 exponent. So if I did the 243, and then there's a exponent button here, and I guess I could even use parentheses and put 1/5, a 1/5 exponent is a 5th root. So this should say, when I press equals, this should say 3. See? The 5th root of 243 is 3, and then you square it to get 9. Or you could do 243 squared, that 59,000 number, and then if I do the 5th root of that, 1 divided by 5, that's 9 too. It works both ways. It's just the really larger numbers are harder to work with. You make things smaller. I could do 3 squared in my head, where who knows what the fifth root of 59,000 is without a calculator. So that answer is 9 both ways. So similar deal, x to the 3 halves equals 125. This problem's just like number 6, just different numbers. X to the 3 halves is 125. So you want to do the opposite exponent of 3 halves, which is 2/3. 2/3 to both sides. That way the 3's cancel and the 2's cancel, and you have x by itself. This, you want to make this a radical. Fractional exponents are radicals. It looks like 125 squared if I get rid of the fraction part. So it should still be 125 squared. It's the denominator part that becomes a root. So it's usually easier to do the root first. I need to break 125 down until I get 3 of exactly the same thing. And it definitely divides by 5 if it ends with a 5. And turns out that's 25. 125 divided by 5 is exactly 25. And 25 is 5 times 5. So there's 3 5s in 125. So that's what it takes. Cube root, you get 3 of the same thing, and that's 1 on the outside. And you still have this square here, so you do that last. The answer is 25. So whether I do the cube root of 125, the cube root is a 1/3 exponent, 1 divided by 3. That is 5, and then you square it at the end to get 25 for the answer. Or I could have taken 125 and squared it first and got a really big number, 15,000, but then the 1/3 power should tell me that the answer is 25 this way too, and it is. So half of this assignment here, homework 17, half of it had x's for the base and numbers in the exponent. The other half was the other way around, where the base was a number and the exponent had an x. Okay, so that one is homework 17. Homework 18, logs. Okay, logs are the opposite of exponentials. And they can go back and forth between each other. So rewrite the expression log base 3 of 9 equals 2 in an equivalent exponential form. Here's how, you're not solving anything here when there's all numbers, but this is read log base 3 of 9 equals 2. There's 3 slots of a log. The low down number is called the base. Log base 3 is how you read this. Log base 3 of 9 equals 2 is how you'd read that out loud. The 9 is in the domain slot. In algebra, we always have a domain and a range. The answer is always the range. But another thing that helps is a log, they have a lot of rules and properties that are very similar to the rules of exponents. So I say to myself, a log is an exponent. And if you remember that little phrase, a log is an exponent, you can find the exponent because it's not in an obvious spot. A log is means equals in math, is an exponent. There it is right there. That's the exponent. So when I have a log equation that has its 3 parts, this is called the log form of this equation. There is an equivalent exponential form that looks like the problems of the last homework. And it has 3 parts too. It's these same 3 numbers, 3, 9, and 2. They're just in a different order. So you say to yourself, which of these 3 things is a base? The 3 is. In exponential form, that's the regular size number. Which of these 3 things is an exponent? A log is an exponent, so the 2 is an exponent. Everybody, even as low as junior high, knows that an exponent's that little number that's raised up high. And then you can just say to yourself, which number haven't I used yet? I haven't used the 9 yet. And isn't it true that 3 squared equals 9? You should get a true statement down here. If you got 2 to the 3rd power equals 9, that's not true. 2 times 2 times 2 is not 9, it's 8. So if your statement is false, you definitely did it wrong. So you're not solving anything, we're just rewriting this in a different format. There's problems later where we do solve log equations and they can get complicated. So if we switch them to exponential form, it makes things easier. Or there is cases where we need to switch an exponential back to a log too. So the exponential form, not the answer, but the form is 3 squared equals 9. So same deal. Log base 2 of 1 equals 0. So let me do it over here. Log base 2 of 1 equals 0. 3 parts of the log. There's 3 parts of the exponential. So log base 2, this is the one that's the base here. That's the regular size number here. A log is an exponent. There's the exponent in the log format. That's the number that goes up high over here. Everybody knows that. And then I haven't used the 1 yet. And it's true that 2 to the 0 is 1 because anything to the 0 power is 1. If I somehow had it another way, like 1 to the 0 equals 2, that's not true. 0 to the 1 equals 2, no. 0 to the 2 equals 1, no. So if you tried any of the other combinations, it wouldn't even be a true statement. So 2 to the 0 equals 1 is another format of the original log equation. Now they should have us go the other way. Yeah, see, now we're going the opposite way. Now we have an exponential equation, and they want us to translate it back to the equivalent log form. Same idea. All you have to do is find the base and the exponent. That's the key thing to both directions. 5 equals 625 to the 1/4 power. Remember, fractional exponents are radicals. But that's true if I do 625 raised to the 1 divided by 4 power. When I press equals, it should say 5. See, that is a true statement. 625 to the 1/4 power is 5. The base in this format is the regular size number that's attached to the one that's raised up high. Clearly, the one raised up high is the exponent. So now we're going to write the log form, and you just put log for log. In the log format, the base is written down low. So where was the base here? The base is 625. That's the down low number. A log is an exponent, so the exponent 1/4 goes over here. So that's the exponent, that's the base. If you know in both formats where's the base, where's the exponent, then you can translate back and forth. Many students find these problems easy. So then you put the 5 right here. It's the only number I haven't used yet. So that's, again, you're not solving anything. You're just trying to write this in an equivalent format. Log base 625 of 5 equals 1/4. So I think you can, sometimes they have an LOG button down here, but I think you can just type LOG, and then you need a subscript. You know how you have this exponent button? This is the subscript button. That's how you get the 625 down low. Now you need to right arrow and get back up to the main level. And then this was where the 5 was, and then equals 1/4. Probably one more of these. Yeah, so they tried to make this one complicated by using no numbers at all. P equals u to the m. There's 3 parts right there. P equals u to the m. Obviously, that upper raised number is an exponent. The regular size number attached to that is the base. The base and the exponent are always together in that format. So log base goes down here, so that's the letter u. A log is an exponent, so this was the base. The equals part in a log is the exponent, which is m. And then I haven't used p yet, so that's the last slot. So you don't even have to know all 3 slots. You just get the base and the exponent, and whatever's left over by process of elimination is the last one. So log base u of p equals m. Log, do the subscript, base, I think you need a capital U because that's what it is over there. Of P, oh no, it's a capital P, sorry, capital P equals M, the exponent, which is not a capital letter. Okay, evaluate without using a calculator, and in fact, you may not be able to use a calculator on some of these, so that's why you should learn how it's done without one. Log base 10 of 100 equals blank is the question. If any of the 3 slots are blank, and there can't be more than one blank, but if one of the 3 is blank, I just put an X in that slot because that's what I want to find X. Now I've got my 3 parts of a log. Let's change it to the equivalent exponential, and then it's going to be exactly like homework number 17. So this is the base, log base 10. Here's the base in the exponential format. A log is an exponent. There's the exponent. Clearly, that's the number raised up high over here, the slot raised up high. And what haven't I used yet? The only one I haven't used is the 100. Now you can finish this, because now we can do like last homework. Is there a way to make 100 look like a 10? 10 to the first is 10, but 10 squared is 100. So I can change the 100 to be 10 squared since they're equal to each other. 10 to the x equals 10 to the second. The 10s cancel out, and x equals 2. I don't even have to solve because it's already x. So log base 10 of 100 equals 2. It's not so obvious why that's the case. So that's why we switch to exponential, where you do something that you're more used to working with, and then you can find the answer. So this is the same thing. Log base 10, this is number 5, of the fraction 1 over 1,000, but that's still just one slot of the process, equals what? So I'm going to put an x there again. Circle the 3 parts. This is considered all together. Log base 10. A log is an exponent. So in exponential, the base is the regular size number 10. A log is an exponent. The exponent is the raised up high number. And I haven't used 1 over 1,000 yet. Now, can we make 1,000 look like 10? Let me continue here. We got the first two. It turns out 10 to the third, that is 1,000. 10 to a power is a 1 with as many zeros as the exponent. So 1,000 is 10 to the third because it has 3 zeros. The only issue is I can change that. That's fine. I can change 1,000 to be 10 to the third. So now the bases are the same, but they don't cancel out unless they're at the same level. You can't cancel one that's in the bottom of a fraction with one that's not in the bottom. We need to have some way where they're both at the same level. So here's a rule of exponents from the past that you're used to doing the other way. In the past, they would tell you never leave a negative exponent in your answer. And if you got 10 to the negative 3, they would mark it wrong if you didn't put 1 over 10 to the positive 3. That's how negative exponents work, is they make the base switch to the other half of the fraction in order to make the negative exponent become positive. Negative exponents have nothing to do with negative numbers. 10 to the negative 3 isn't even equal to a negative. But now we want to go the other way. Before it was frowned upon to stay here, now we want to go there. I can change 1 over 10 to the third to 10 to the negative 3. And the only reason I want to do it, I don't need it necessarily as a final answer, but now the 10s are the same and they're at the same level. So now the 10s cancel, and x equals negative 3. Or in other words, the blank is negative 3. So sometimes when they tell you not to do something in a math class, sometimes later in another math class, it's actually needed to be done, even though it used to be counted wrong. Okay, same kind of problem. Log base 5 of 625 equals what? Log base 5 of 625 equals what? Here's the base, log base 5. That's the regular size number. A log is an exponent. There's an exponent. And I haven't used 625 yet. Can we make 625 look like a 5? Always try to make the bigger number look like the smaller one. Well, let's see. 5 to the first is 5. 5 squared is 25. We saw 5 cubed earlier today. That was 125. So what's 5 to the 4th power? 5 raised to the 4th power? Aha, there it is, 625. So once you know the smaller base, this is the first strategy you should try, is can I keep increasing the exponent by 1 until I get this bigger number? If this jumped from 125 to say 725, then you skip this number, then you know that strategy doesn't work. and maybe you're not going to get the kinds that don't work at this point, but we'll see if that happens. So 5 to the 4th is the same thing as 625. And now the 5s are the same, and they're at the same level, so they cross out. X equals 4. And X is the blank that we're trying to fill in here. I just call it X. Okay, this is a special case. So there's two properties of logs where if you have log base b, we'll just call it b for general, log any base, and then if in the domain slot you have another b, and then let me put an exponent here like x. This answer is x. In other words, all of this cancels out. If the domain base is the same as the log base, they cancel out. And all that's left is the exponent. And if the exponent is blank, a blank exponent's a 1, so then the answer is 1. So if you do log base 7 of 7, that answer is 1, because there's a 1 for that exponent, and this part just cancels out. It also goes the other way with exponentials. If you have 7 to the log base 7 of whatever, these all cancel out, and you get just x that way too. And then there's two special kinds of logs. Log base 10 is normally not written that way, even if I don't have the idea where they cancel out. Log base 10 of x, there's a shorthand way to write that. We just write log x. If you don't see a base, it's not a 1, it's actually a 10. Everything in math has a blank version. Most blanks are 1s, like x right here. If you don't see a number in front of the x, it's a 1. If you don't see a number in the exponent, it's a 1. But like in a square root, if you don't see a number there, that's a 2 right there. There is no 1th root. So log, same deal, their blanks are 10s. So somebody decided, okay, log base 10, we're going to call that that's actually called the common log. It's the most common thing that can happen for logs. So it just helps if you're writing it, or back in the day they were using typewriters, and it was hard to do subscripts on a typewriter. So somebody said, let's just leave that blank and it'll be understood to be a 10. And the reason 10 is the one that's left blank is because us humans have 10 fingers. If we lived like the Simpsons with 8 fingers, then base 8 would be the common log. And then there's one more called natural log. Natural log is log base e of something like x. And this is written ln. ln is a shorthand way to say log base e. Those are the two most common ones. And many calculators have a log button and an ln button. So this is log base 10 and this is log base e, and they don't put any other logs on here because it would just take up too much space on the keyboard and in the memory bank. So if you get log base 10 or log base e, calculators could get you decimal versions, although that might not help you on a homework answer. But any other base, you definitely couldn't do it in a calculator. So this is the idea right here that I was just showing you on number 8. There's nothing to do here because ln e to the negative 14 equals what is what they're asking. Well, if you know that ln is actually log base e of e to the negative 14, this all cancels out and the answer is negative 14. It's the same idea as this one here. It's just that this exponent was a 1 and this exponent's a negative 14. So if the log has a base that's the same as the domain base, then the answer is whatever the exponent is. And if the exponent is blank, then it's a 1. And I told you it works this way too, although that D's kind of in the way first. So there's a third property of logs that says if you have log any base of x to the m power, you can bring the m down in front and multiply to the log. Or if a number's in front, you can move it up as an exponent. So this goes both ways. Move it up as an exponent or move it down as a times. And what they gave me here is 2 to the d times log base 2 of g. And there's that other property of logs where if you have a base and then in the exponent is a log of that base, all of that cancels out, leaving this as the answer. As long as it's this exactly, you got to have 7 log 7. 7 to the log base 7. The problem with this one is the d is kind of in the way. But I could use this property of logs and say, oh, wait a minute, that m could go up there and become an exponent. So move this d up. And it's just g to the d power. We don't really care what that equals. I want to use this property of logs where the base 2 can cancel out a log base 2 if it's up there in the exponent. And then this is literally the answer, g to the d power. So then you don't even have to do any work after you know those two properties. Okay, log base 2 of x equals 3. Find the value of x without a calculator. So the point here is that the x can move around to different locations. We did a number of problems where the equals was the blank, and I just put an x there. Remember that one, and this one, and this one. If the answer is blank, I always called it an x. But this number or the base could be an x too. And then they'll actually put an x for it. They don't leave it blank usually. So number 10, log base 2 of x equals 3, solve for x. This is, again, let's translate this over to the equivalent exponential form. Circle the 3 parts you have of this log right here. Log base 2, so that's the base. A log is an exponent. There's the exponent. I'm in log form right now. Let's translate it to exponential form. So which one's the base? The base is 2. That's the regular size number. A log is an exponent. That's the 3. Which one haven't we used yet? We haven't used x yet. And at this point, you might have to solve for x. But here we got lucky. The x is already by itself. So this will be the answer, except we could simplify 2 to the third and make that 8. Always try to make answers easier if you can. 2 raised to the third power is a little messy to leave that. So 2 to the third is 8. 2 times 2 times 2. Or sometimes the base is the x. So they're probably going to do that here in one of these last 4 problems. No, okay. So evaluate without using a calculator. Okay, so they've got log and they've got ln. This is the common log. Oh no, this is using a calculator. I'm sorry. Okay. So this is common log and natural log. This is exactly what I was saying. If you get one of those two, they're the two that are in a calculator. So log, that's base 10. Ln is base e. So in this calculator, I think what I have to do is I have to type the number first, 2823.5, and then I hit my log button. And then round to 5 decimals. Okay, 3.450, 787. So I went to the 6 decimal place. Since that 6th one is 5 or higher, you got to add 1 to the 5th one, which is add 1 to the 8 and make it a 9. So if the log is really complicated, then the only way to do it is with a calculator. But a calculator will only work on log base 10 and log base E, common log and natural log, and you should only do a calculator answer when they ask for one. Because if you do it when they don't want it, they'll just count it wrong even if your answer is approximately equivalent. So now we need to do, I'm going to type in 0.0883402. And then it's log common log, round to 5 decimals, negative 1.053. There's the first 3 decimals. 841. This time the 6th number is not 5 or higher, so then I don't have to add 1 to the 4, just leave it like that. ln, okay, so now type in 768.23, hit ln, 5 decimals, 6.644. .089. The 9 will add 1 to the 8, making that a 9. Whoops. I didn't go over the 8 is what happened. The 8 should become a 9. And then finally, ln of 0.062517 ln, negative 2.772, 316, 316. The 6 is big enough to add 1 to the 1 and make that 1 a 2. So there are a few times where you do that. Okay, here's what I was saying. I wasn't sure if they were going to throw this at you yet or not, but they did. Sometimes you cannot make the bases the same. 10 to the x equals 29. The normal strategy is try to make the bigger one look like the smaller one. But powers of 10 are 10 and 100. I don't have 29 in that list. And if you skip the one you're trying to get to, you're never going to get it if you keep going higher. So I can't make 29 look like a 10. Sometimes you can make both numbers smaller bases. Like say you had a 8 to the x equals 16. There's no way to make 16 look like an 8, but we could make them both powers of 2 potentially. Since 2 to the 3rd is 8 and 2 to the 4th is 16, I could change them both to 2s. And then eventually the bases would cancel out. But literally sometimes like this 10 doesn't go down any farther. It could be a 5 or a 2, but they're not going to go into 29. So then all you can do is put either an log or an ln on each side of the equation, and in most cases it really doesn't matter. If they're regular numbers, I use log, and only if there's an e would I use ln. Because what this does is we're trying to solve for x. The ultimate goal in algebra is to get x by itself. You're never going to get it by itself if it's stuck up in an exponent. And there's only 2 ways to get it out of the exponent. Make the bases cancel out or use logs on each side. Because then I can go back to that property of logs where the exponent can move up or down as needed. I've got it up here. I want to move it down in front now. This version of it. So that x can come down in front and be x times log of 10 equals log of 29. And then you can divide both sides by log of 10. And now it depends if they want a decimal answer or not. Don't put a decimal unless they ask for it. X, this could be the exact answer potentially. Especially in higher level math, they prefer the exact answer. They don't like decimal answers except when it's absolutely necessary. So we got to check. It does say round to 4 decimal places. So then you can do a calculator version of the answer. So I've got 29 log divided by 10 log equals. And this is how many decimals? 4. So 1.4623, but after the 3 is a 9, so you got to add 1 to that 3 and make it a 4. 1.4624. So putting a log on each side of an equation can be helpful because it can get an x out of an exponent like that when it's stuck up there. And as I mentioned, if I have regular numbers like 10 and 29, I put log. You could still do ln if you want. But if one of the bases is e, then I definitely use ln. E to the x equals 5.665. Put an ln on each side. Then you get to bring your exponent down by the property of logs. And then technically you could divide both sides by ln of e if you want and type it in a calculator like I did on the last problem. But it turns out, remember ln e? ln e is the same thing as log base e of e. That just all cancels out. That's equal to 1. So then if you realize this was 1 right here, you wouldn't have to divide by anything. You would have just had this at that point. Oops, forgot a 6 there. And do they still want a decimal here? Yes, 4 decimals. But all I need is ln of 5.665 ln. I don't have to divide by ln of e. You could, but then you're just wasting your time because it's going to be equal to 1. So 1.73430, the 0 is not big enough to add anything, 1.7343. And finally, we've got a 2.013 to the 9t equals 3. We're clearly not going to make those bases the same. 2.103 to the 9t equals 3. There's no way 3 is ever going to look like 2.1. And I don't see any e's here, so I would just put log on each side. Now you can bring the exponent down in front. Log of 2.103 isn't anything special, unlike log of 10 or ln of e. So then I can divide by the log. And we'll just end up typing it into a calculator like 2 problems ago. But one other thing too is there's a 9 times this t, so I can divide by 9 at the same time. Or you can do it afterwards too. Like you could do this first, and then wait, and then divide by 9 after that. So if I do the logs first, 3 log divided by 2.103 log equals, then divide by 9. And round to 4 decimals. So 0.1642, the next digit's a 1, so we don't have to add 1. 0.1642. Okay, so that's homework number 18. We're done with that one now. And let's take a quick look what's going on in this homework 19. It's kind of weird how they got a homework with just like 1 problem in it. But okay, 100, 100. I'm looking over here where my scores are. 100, 100, 100, 100. I got hundreds on everything this week except 19 basic calculator, and then there's a quiz you can do as soon as you're at least done. But there's only 1 question here, so I don't know what's going on here. There's a typo in the formula the instructor uses in the third to last video. Okay. So apparently they want you to watch some videos here. There's a minus sign between the 1 and the RN when he inputs the quantities. Here's the calculator for the video. You use the correct formula, 1 plus R over N. Okay. So what do we got going on here? There's apparently 3 videos to watch. I don't know how long they are. Use the compound interest formula to find the future value. Okay. Okay, so this formula, there's 2 versions of it. This is how you like put money in a bank and how it grows. A stands for the future value. And then P is the present value. So say I put $1,000 in the bank. I put $1,000 in the bank right now. That's the present value. And then they are correct about that. I haven't looked at the video yet, but apparently the person in the video puts 1 minus, but there's actually a 1 plus here. And then what you get is R over N to the NT power. This is one way to write it if you want to see all the individual parts. R is the interest rate. T is the time in years you leave it in the bank. And then N is how many times per year the interest is calculated. Now a shorthand way to write this is they'll write 1 plus I, where I is this fraction, but the problem with that is you have to know that it's a fraction. It doesn't look like a fraction here. And then they just call this whole exponent N instead of separately NT. So that's what they're giving me here. I'll have to do it this way. P is $2,000. Somebody is putting $2,000 in the bank right now. Since they gave me I has already been divided, 0.051. So somebody did R divided by N for us already. And then somebody multiplied these together. I guess we can call these M's just so they're not confused with N. So R over M is the number of times per year you do it. And then M times T is your total number of times you're getting interest. And that's apparently 20. So the one nice part here, if you follow order of operations, you should definitely be doing the parenthesis first. But one nice thing is 1 plus a point decimal is literally 1 point, whatever that decimal is. So I did inside the parentheses first. Then according to order of operations, we would do the exponent second. And I guess that's the point of this assignment, is learning how to use a calculator like this. So if I type 1.051, oops, you can't see it, 1.051 raised to the 20th power. And that's going to be a big, long, messy decimal. But that's okay because the calculator has it there. And then the only thing left is to multiply by 2,000. So you did the parenthesis first, then the exponent, and then finally the multiplying last. So times 2,000. That's the correct order. You don't want to do the times first before you do the exponent. So this would be how much money is in your account 20 periods from now. So it depends if they do it monthly or quarterly or weekly or daily. But 20 different times you're going to get interest, and your $2,000 will grow to $5,408.59 if they want cents. Sometimes they want dollars, sometimes they want cents. That's a pretty good deal. You started with $2,000 and you more than doubled your money. It's all free money, all that extra $3,400. So that's what it's worth in the future. You come back so many years from now, $5,408, round to the nearest cent, 59 cents. So I'm not sure if, I guess you have to watch these videos. I don't know how long they are because I just did the one problem, and from my video you would know how to do that one problem now potentially. but notice it only gave me a score of 25% up here. And you need at least a 70 to be able to take the quiz. So I guess I was supposed to come here on Media 1 and click this. And watch this video. It's only 2 minutes long. I think this is the textbook author, so she's explaining this, and she's got the right formula there. Does it say it gave me credit just for opening that? And then if I open Media 2, let's use the TI-30X calculator and the loan payment formula. And then if I open Media 3, and now I've already got 75%. So you can watch these if you want. They're only 2 minutes long each. Right there, see there's a mistake right there. Here's 1 plus, but then somehow it got switched to a minus by accident. And I don't know if that means it's wrong all the way at the end. Let's see if he corrects his mistake here.
And immediately what's after the 360, the units on that. 0.07. I'm going to come over with the right arrow key until I get to where I would like that one key that will delete it.
So yeah, I don't know
and also
if he corrected himself or not.
For insert. That's in blue ink. That means we hit the blue second key first.
So that's fine. If you don't even have one of these types of calculators, this doesn't really apply to you anyway. So there, now I have 100% on that. So yeah, I was right. This is a pretty short assignment. The purpose of it is one example of a business setting where you're making interest. And then they've got 3 videos showing how to use a special type of calculator. I think the college likes that calculator, so they recommend that to students. But if you notice, I don't even have that calculator myself. And if you're just using like a scientific calculator on the computer, that's good enough for this class. So this assignment's more of an optional thing, but you have to get at least 70 to take the quiz. So just click those medias real quick just so you get credit for that. And you can watch them if you want, but it's not a big deal if you don't. So there, we're all done with this week's homework. And now you got quiz 3 to take at some point, at least once, until you get a grade you're happy with. Now, next week's our last week for this class. We still have 2 weeks to go for the other one. So next week, it'll be pretty short. Apparently, we're going to do homework 20 on Monday, 21 on Tuesday, and 22 on Wednesday. And then you'll get Thursday and Friday to take the quiz. And that's basically the end of this class. You still get credit for, your grade could still change later because the review for the final in the other class counts as a grade in this class. So your grade will not be done fully in this class at the end of next week. But next week is the last time we do anything for this class. And once you've completed quiz 4, then you can put all your attention into the 1324 class. So that's it for Wednesday, August 3rd is what this video was for. And then we got 3 more videos to go, and they might all be pretty short ones if I'm just doing one homework each day. So see you next Monday for homework 20.